break, which I've subsequently destroyed. I want to thank, I said at the beginning we had a star-studded cast. I want to thank all the previous speakers. I think I was proven to be true until this very moment. Today I'm going to talk about some research. It's been one of my more recent research muses. For about the past 5 or 6 years, I've been looking at pharmaceuticals in the environment, and in particular, my interest is in pharmaceuticals in subsistence species used by the Grand Portage Band of Lake Superior, Chippewa, which is the Indian tribe for whom I work. I initially became interested in looking at pharmaceuticals in the environment as a consequence of looking at this particular graph. This graph indicates biomass of 3 Great Lakes from about the late 1980s to present. There's about a 90% decline in biomass across all 5 Great Lakes. I was only able to fit 3 on this particular graph. Interestingly to me, we have different explanatory mechanisms for each of these Great Lakes, all of which are plausible, but from a broad scale perspective, it looked to me like there may be some sort of larger environmental phenomenon going on, and I wondered if it may be related to toxins in the environment. I don't have any data to support that, but that's really what triggered my interest in this line of research. My interest is related to how pharmaceuticals may be affecting fish populations themselves, and then ultimately what the potential risks to consumption might be, either through reduced populations such that rights to harvest fish can't be exercised by tribal members, or the direct risks of consuming different types of toxins in fish species that are consumed. I'm going to tell a couple stories about pharmaceuticals in the environment because I find them fascinating. This first story is about an a non-steroidal anti-inflammatory that was used in the agricultural industry, primarily in India. It's a medicine called diclofenac, and it was used for treatment of livestock in about the 1990s and was found to be lethal to the gyps vulture. It caused visceral gout and caused renal failure to the point that one carcass in which diclofenac was used out of 760 livestock carcasses on the landscape was sufficient to crash the vulture population to the point that it became critically endangered. It is still critically endangered to this day. Interestingly enough, as a consequence of these carcasses on the landscape, 1 in 760 carcasses on the landscape, that was sufficient to crash the population. But because of all the cattle carcasses that were left on the landscape not to be consumed by vultures, wild dog populations in India increased. It led to an increase in rabies in wild dogs and subsequently in humans as well. Cool story. It's a morbid story, but it's an interesting one. In aquatic environments, pharmaceuticals play a significant role as well. In the experimental lakes region of Ontario, an experimental lake was dosed with 5 parts per trillion of ethinyl estradiol. This is the birth control hormone used by humans. It caused the entire minnow population in that lake to collapse. Subsequent to that, the lake trout population collapsed as well. Interestingly, 10 years following that study, both populations actually recovered once the pharmaceutical had left the water body. 30 parts per trillion of an antidepressant called fluoxamine triggers immediate spawning in mussels. Close your eyes, everybody. Imagine if that happened in humans. Sorry. Many of the pharmaceuticals that are found in the environment cause behavioral changes or reproductive changes. Fish behaviors are altered at 1 part per trillion of the birth control ethinyl estradiol. In addition to that, behaviors are triggered by many of the antidepressants. And then some of the chemicals that we see in the environment, when mixed with chlorine, like in a water treatment facility, create highly toxic compounds that also are lethal to fish. We started studying this several years ago in Grand Portage and in northeastern Minnesota. We surveyed 28 different water bodies under 3 different treatment types. Some of these treatment types were known to have wastewater effluent passing into them. Some of them were highly developed but used for subsistence and commercial purposes. Some of these were undeveloped wilderness, literally 0 development in the watershed whatsoever. And then we also looked at 6 Lake Superior sites as well. I focused most of my results today on the Lake Superior results for 2 reasons. This is a Lake Superior Committee meeting, and second of all, I've never presented them before, so I'm excited to do so. The fish from which we collected samples in the inland lakes were walleye and yellow perch. In Lake Superior were lake trout and cisco. And we chose these because these are species that are used for subsistence by the Grand Portage tribal members and other Chippewa, but also they're recreationally harvested and consumed species. The map here indicates the locations from which we collected samples of tissue, fish tissue, water, and sediments across the 1854 ceded territory, primarily within the Great Lakes watershed, and then the sites that we've also evaluated in Lake Superior itself. All the fish samples were processed with a meat grinder using sterile technique and then submitted for analysis. I want to quickly go into our results. I want to leave some time for questions for Ben Rook because we missed his opportunity earlier. In our water samples, we screened, in all of our samples, we screened for 160 different pharmaceuticals and 16 different hormones. Of the 140 chemicals of emerging concern that we screened for in water samples, we found 93. About 66% of the ones we screened for we have found in water samples, ranging from 1 to 77 detects per sample. Wastewater effluent had much higher rates of detections, which is not surprising. In our sediment samples, similar results. We found about 40% of the pharmaceuticals we tested for in sediments, ranging from 2 to 59 detections. Again, wastewater treatment sites had the highest levels and the broadest range of detections. And in our fish samples across all species and all samples, we found about 18% of the pharmaceuticals we tested for in fish tissue samples. Typically, there were between 1 and 7 different pharmaceuticals in fish samples. Don't worry too much about the x-axis here. These are all the different chemicals that we have found in all three media types of sediments, waters, and fish. We have found 109 of the 141 that we've tested for across all sample types and media. I'll go into these in a bit more detail in just a minute here. The state of Minnesota has been a leader in pharmaceuticals research in terms of pharmaceuticals in the environment, and they've developed a technique by which they prioritize what pharmaceuticals in the environment are the ones that we should be most concerned about, which is great because it saved me a lot of literature review. But they use this process called aquatic toxicity profiles, which looks at the weight of evidence in the literature and in laboratory studies to determine the effects of these specific contaminants and what those effects might be on biota. They do this by looking at some chemical parameters, the half-life of the chemical, its level of toxicity, and its ability to biodegrade. That's as much detail as I'm going to go into this process, but I'll show you some of these important pharmaceuticals in this next slide. The high priority contaminants, and in this slide and in subsequent slides, will be indicated by a brown star because they are likely from wastewater effluent. The ones we were concerned about primarily are hormones, estrone and progesterone. These are some, this is a type 2 diabetes drug. DEET is an insect repellent, obviously. And these are the chemicals, same thing. Clotrimazole is an antifungal, and triclocarbon is an antibacterial. All right, so let's look at some of the Lake Superior water samples that we looked at. The list here shows the types of pharmaceuticals that are found in Lake Superior water. We collected samples, 2 sets of samples off the Duluth entry, and then the other samples were in much more remote parts of the lake. And I'll be able to contrast those, I believe, in the next slide. But there are a number of pharmaceuticals present in Lake Superior, and there are several of concern. These are the pharmaceuticals that we found in the Lake Superior fish samples. So these are samples of cisco and lake trout, and about 18 or 20 different pharmaceuticals, including hormones, steroids, antibacterials. This one's an interesting one. Iopamidol is a medicine that's taken to make organs opaque under x-rays. one would think it wouldn't be very prevalent in the environment, in fact is ubiquitous. And I found out more recently why it's ubiquitous in the environment. Every dialysis patient prior to dialysis on a weekly basis has to take iopamidol prior to their evaluation. And so that's the mechanism by which it's entering the environment, is through excretion primarily. So if you contrast the sites in Lake Superior, I mentioned we've taken a few samples from off of the Duluth entry and a few samples from much less developed parts of Lake Superior. There's a striking difference in the number of detections of pharmaceuticals based on how close you are to human development. Seeing Gene Adams in this audience makes me laugh about the fact that 20 years ago I was doing multivariate ordinations and complex analysis, and now I'm showing histograms and bar charts without error bars. In looking at the fish samples, there's not quite as stark a contrast. Interestingly, in fish, we find about the same number of contaminants. Whether they're developed or not, we found this in our inland systems as well. There are typically between 1 and 10 contaminants, pharmaceutical contaminants found in fish tissues, no matter where or how we sample. These are some of the findings from lake trout. It looks like we found DEET everywhere. DEET is ubiquitous. It's been found in every single sediment sample, every water sample, and every fish sample we've ever taken. It also is one of the contaminants of concern from a biological perspective as well. Looks like we found some hydrocortisone, which is a steroid. Again, iopamidol, metformin, which is a type 2 diabetes drug. And then these ones towards the end, venlafaxine, another antidepressant. But these are the ones that have behavioral impacts on fish. Cisco, it's a similar suite of chemicals, but again, about 10 chemicals that are present in Cisco and Lake Superior. This image just shows the overlap in chemicals between Cisco and lake trout, but they're relatively similar. There are a few differences between the two. In the sediment samples that we found in Lake Superior, androsterone, which is a weak male hormone, it's been shown to have increased lipid and protein content in catfish under treatment. It's also shown to have increased aggression in prepubescent boys. DEET, mestranol, which is this is a synthetic hormone, causes sex reversal of fish. Concerning in sediments is clotrimazole and myconazole. Both of these are antifungals. One would think that fungus that are naturally occurring in sediments might possibly be affected by these. Amitriptyline, I think this too is an antidepressant. It's been shown to cause premature hatch and small sizet hatch of zebrafish. Zebrafish are a surrogate type of fish used in laboratory studies because they're surrogates for other more common species of fish. Sertraline and venlafaxine are both antidepressants. So these are the results of our detections across all media types, inland and Lake Superior. Obviously, wastewater treatment effluent locations have much, much higher numbers of detections, but the undeveloped and developed actually have similar numbers of detections across all three media types, which indicates some of these things are entering the environment, obviously atmospherically, because there is no effluent in undeveloped areas. These are the findings in fish. Again, the number of detections in fish are similar across all types of anthropogenic development. This indicates here the different classes of drugs that we're finding in the environment. And to me, this graph in particular shows the state of human society as seen in the environment. We see artificial hormones, we see antidepressants, we see antibiotics, which also can cause antibiotic resistance in wild fish and other organisms, insect repellent, and blood pressure. Those are the top players. This is somewhat concerning to me because, as I mentioned earlier, the effects of these pharmaceuticals on non-target biota can be much greater at much, much lower dosages. These are the artificial hormones that we've found in the environment. And the importance of these is not necessarily seen in this graph. These are the types of hormones, but the importance is here. These are the classes of North American fish species in which exposure to artificial hormones can cause severe aberrations in gonadal development or sex reversal. We have sturgeon family, eel family, minnow family, catfish family, salmon family, pike family, and some perkids. These are North American fish, all with potential to be impacted by hormones in the environment. So the things that concern me as a biologist, and in particular as a tribal biologist, is that we have pharmaceuticals that are ubiquitous in the environment. The effects of these are relatively unknown. This area is not getting sufficient funding for research. There are not enough laboratory studies being done, and this is the direction that we really need to go with this type of work. I'm concerned about the number of hormones and antidepressants that we find in the environment. Desogestrel is a anti-cancer neoplastic drug, causes changes in RNA. Mestranol, a human hormone found in 60% of our samples. Ubiquitous fish tissue detections, there are no samples in which we found nothing. And the concern for me is how are we going to ever actually manage this, either from a policy perspective or from a pharmaceutical management perspective. An interesting study was done in Norway where they found that I think 80% of pharmaceuticals that were administered in a hospital were excreted in the hospital as well. Hospital wastewater treatment may be a low-hanging fruit to reduce significant amounts of pharmaceuticals in the environment. It's certainly something that should be explored, in my opinion. In addition to that, how pharmaceuticals are delivered is another opportunity to manage how pharmaceuticals end up in the environment. Thinking through every single pharmaceutical commercial one ever sees, you see a list of side effects that is 10 times longer than the effects of the pharmaceutical on whatever its biological target is. People end up discarding these pharmaceuticals once they achieve some of these side effects, and they're ending up in the wastewater stream. So those are the things I would manage, is maybe hospitals and how pharmaceuticals are delivered. We may want to implement some sort of water quality standards for pharmaceuticals as well. And I left myself 2.5 minutes for questions, for me or for Ben Rook.